Hello there, Mr. Sutton here, bringing you the AB Calculus 412 Extra Practice number 3 solutions on motion. On this problem, for time greater than or equal to 1, position of a particle on the x-axis is given by this p of t function. We want to know at what time in the interval from 1 to 16 the instantaneous velocity is equal to the average velocity of the particle. Okay, so we need to figure out the average rate of change for position then, because that's what the average velocity is, over the interval from 1 to 16. So we need to do p of 16 minus p of 1 over 16 minus 1. P of 16, that's going to be here, and let's just rewrite this denominator, we'll deal with it in a minute. P of 16, that's the square root of 16 minus 2, so 4 minus 2 is 2. And now p of 1, that's the square root of 1 minus 2, well, that's going to be negative 1, but we're subtracting it, so that's actually 2 plus 1. So this is going to be 3 over 15, which is 1/5. And now we needed to know at what time the instantaneous velocity was equal to this average velocity, kind of like a mean value theorem sort of setup. So we need to find the instantaneous velocity formula for p of t. We need p prime of t, and then we're going to set that equal and solve to the 1/5 that we just got. So the function originally is t to the 1/2 minus 2. So using the power rule, we can write p prime as 1/2 t to the negative 1/2. And again, we want this to equal 1/5. We want to know what time that happens. So just using a little algebra to solve this, I'm going to multiply both sides by 2. And then, with 2/5 over there, I'm going to raise both sides to the negative 2 power. That'll cancel out the negative 1/2 power. So we have negative 2/5 to the negative 2, or actually just positive 2/5 to the negative 2. So that means I have to take the reciprocal of this, which is 5 over 2, and then square it. So that's going to be 25 over 4, giving us answer choice C. For this one, a whole lot of reading. The rate at which water leaks out of a tank in gallons per hour, modeled by R, differentiable function. And let's see, of the number of hours after the leak is discovered. So we want to know which is the best interpretation of R prime of 3. So R prime of 3 isn't talking about the rate at which water is leaking out of the tank. It's talking about the rate of water leakage. So R prime of 3 is basically saying the rate that the leakage rate is changing at 3 hours. So let's see which answer choice has that. So choice A, the amount of water in gallons that is leaked out. No, that's not it. In fact, let's talk a little bit more about units. If R prime of 3 is the rate of leaking, well, the rate of leaking is gallons per hour. So the rate that's happening is going to be gallons per hour, so gallons per hour squared. So choice A is wrong just all the way around. Choice B, amount of change in gallons per hour in the rate at which water is leaking. So this is kind of like the change in R, like R3 minus R0, so that's not really what we're looking for. Choice C, the rate at which water leaks from the tank in gallons per hour. Well, that's just plain old R. R itself is the rate of leaking. Choice D, rate of change of the rate at which water leaks from the tank in gallons per hour per hour. Now, that's the one that we're looking for, so choice D. For this problem, acceleration of a particle moving along the x-axis is given by this formula here, between time 0 and 8. We want to know at what value of t is the velocity decreasing most rapidly. So velocity decreasing, that's talking about acceleration. In particular, we want to know when the acceleration is at a minimum value. So we basically want to find the absolute min for the a function on the interval from 0 to 8. Okay, well, in order to do that, there's a few things we could do. One way, if you wanted to be really cheap about it, would be to just plug these values in to the a function and see which one comes out the smallest. So, I mean, that works on multiple choice. I'm going to do it the legitimate, longer way, but if you're on a hurry on this test, that would probably be the fastest way to get your answer. I mean, these are all between 0 and 8, so just take the smallest value. But doing it the longer way that you could use on a free response problem as well, we would find a prime of t to get some critical values, and then we would test those along with the endpoints 0 and 8 in the a of t function. So a prime of t then, that's going to require the product rule. So I'll use my box and ribbon here. I've got t minus 8 and sine of t, and the derivatives of those, That would be 1 and cosine of t. And now I'm just going to write a prime of t in a u prime v plus uv prime pattern. So let me use my ribbon here to multiply things in that order. We've got a prime of t equaling sine of t plus parentheses t minus 8 times cosine of t. And now that I've got a prime of t, I'm going to solve this on the calculator. Now, I'm not looking for just places where this thing equals 0. I'm looking specifically for places where this goes from, let's see, we want the absolute min, so we want to go from negative to positive. So if I have a place where we're going positive to negative, that would be a relative max, and I know that can't be the min. So let me go to the calculator now. So here's what I've got in my y equals for my calculator. In y1, I actually put the original a of t function, because when I find the candidates for my candidates test, I'm going to have to plug them back into the a function, and y1 will be very helpful for doing that. In y2, I've got the a prime that I just figured out, and I've only selected that. I deselected y1. So let me just graph y2. I'm going to use the interval from 0 to 8. So if you go to Windows, 0 to 8 is what we're looking for. And let me just do zoom 0 to get the perfect window on this. And I'm going to be figuring out, again, I want sign changes from negative to positive. So there's one of those sign changes. I'm not going to test this one. This one I'm going to test. And I've gotten myself off the hook of identifying this middle one as a candidate because I'm talking about this thing changing from negative to positive. So I'm telling them basically, hey, I'm only checking relative mins, not maxes. So let's go through and find these now. Let me do second trace zeros, option 2. And let me go to the one on the far left. Just move my spider over there. And a little bit to the left, press enter. A little bit to the right, press enter. Enter one more time. And, whoops, error bound. What's going on there? All right, let's try that again. My third enter actually works this time. Don't know what happened that last time. But anyway, we get about 1.4200. And I am going to give that a name. I'm going to give that weird number the name A so that I can refer to it quickly on my calculator and on my paper when I need to. So let me just quit out of here, and I'm going to press the store button and store that as alpha A. So now I can go back and test it out when I want to. Okay, let's go back and let's see, second trace again, zeros. And I'm not going to look at that middle one again because that's going to be a relative max. It can't possibly be the absolute min. And now let me go right here, enter, enter again to the right, enter again one more time. Comes out to about 7.0454. I'm going to call this one B. Now you might notice that that number is not one of the answer choices, so it's not the answer, but I'll put it in there anyway. Again, I'm just showing you, for any type of problem, how to solve this. And let me go back to my calculator and quit out of my graph, and let me store that as alpha B. All right, so I've got to test out a few things now. One of my candidates is, of course, 0, so I need to do A of 0. Now, you should very quickly be able to tell what this is going to be, even without a calculator. If you plug 0 in for t, sine of 0 is 0, and that zeroes everything out. So we don't really need to test that on the calculator. This next one, though, we're going to do A of big A here, of this 1.4 number. So let me go to the calculator and do that. I'm going to do alpha trace, pull up my Y menu, and Y1 is where I stored the A function. So I'm going to plug in alpha A for this one. And enter. Comes out to about negative 6.505. So far, that's winning. But let's test the other ones because you never know. Let me test out B now. So A of B, which sounds kind of weird, but it is what it is. So back on the calculator, let me yank my input from before, and I'm going to swap out the A in here with alpha B, just plugging B into the little a function, the acceleration function. We get about negative 0.6592, so 659 and some change. That is not the min, so A, 1.420 is still winning. Now, again, 8 is not one of the answer choices, so it's not going to be the winner, but let's just test it out just to show the candidates test. So if you plug 8 in, this is another one you don't really need the calculator. We have 8 minus 8, which is going to zero out this first part and zero out the whole thing. So that just comes out to 0, just like 0 did. So out of all of these, the absolute min is this negative 6.505 number, and that happens at time A, which is to say time 1.420, which gives us choice B. On this problem, at time 0, storage tank is empty and begins filling with water. For a time that's positive, the depth in the water is increasing at a rate of W of t. So W of t is the rate at which the water is increasing. Which of the following is the best interpretation of W prime of 2 greater than 3? All right, so taking a look at these different choices here, 2 hours after the tank begins filling with water, the depth of the water is increasing at a rate greater than 3 feet per hour. All right, so this would be saying, since W of t is the rate at which the water is increasing, if the depth of the water is increasing at a rate greater than 3 feet per hour, this is W of 2 greater than 3. Choice A is not the prime, it's just the original function, because the original function was the rate at which the depth was increasing. Choice B, over the first 2 hours the tank begins filling, depth of the water is always increasing at a rate greater than 3. Well, this is saying for time 0 to 2, W of 2 is greater than 3. So pretty much, or W of t is greater than 3. So pretty much what we were saying in A, except they're saying that this is true for the entire time period from 0 to 2. And that isn't really quite what the original was saying here. That's not W prime of 2. So choice C, 2 hours after the tank begins filling, the rate at which the depth of the water is rising is increasing at a rate greater than 3. Okay, so this is saying that the rate of the rate is greater than 3. And that's what we're looking for here. Choice C is giving us W prime of 2 greater than 3. And then let's just look at choice D. I mean, we're already here. Over the first 2 hours, the rate at which the depth of the water is rising is always increasing. So this is saying, kind of like choice B, W prime of t is greater than 3 for 0 to 2. Again, not what we were saying with W prime of 2. This is saying at exactly 2 hours, the rate of the rate is greater than 3. So we're going to go with choice C on this one. For this problem, we have a particle moving along the y-axis with a position given by this y of t function. They want to know over the interval from 0 to 4, at what t values is the speed increasing. So to talk about where the speed is increasing, we need to figure out where the velocity and the acceleration of this particle have the same sign, either both positive or both negative. And to do that, we need to do sign analysis on both of those functions. Let's start with the velocity, y prime of t. So that's going to be 3t squared minus 12t plus 9. And I'm going to call this v of t from now on, so I don't have to write y prime. So let's see. We're going to set this equal to 0, find some critical values, and do some sign analysis. I can start by factoring out a 3. That leaves me with t squared minus 4t plus 3. All of that equals 0 still. And then factoring this, numbers that multiply to 3 and add up to negative 4, we've got t minus 1 and t minus 3. So that means our critical values are 1 and 3, both of which are between 0 and 4, so we have to put them both on our v of t or y prime number line, whichever you want to call this. So we've got a 0 and 4 as our endpoints. We don't want to test anything outside of those. And 1 and 3 are our critical values. So I'm going to use this factored version of v to do my sign analysis. Plugging in something between 0 and 1, let's go with 1/2. So that's going to give us a negative and a negative, so positive. And then between 1 and 3, I'm going to go with 2. That's a positive times a negative, which is negative. And then between 3 and 4, how about 3.5 or 7/2? So that's going to be a positive. Positive comes out positive. All right, now let's do the acceleration sign analysis. For that, we need y double prime of t or v prime of t, however you want to think about that. That's going to be 6t minus 12. And setting that equal to 0, we see that the only critical value, if you add 12 and divide by 6, is going to be at time 2. So putting that on a number line, again, we have 0 and 4 as my endpoints, and this is the a of t number line now. Just this one critical value at 2. And I'm going to test things out now in this a of t function. So if I test out something in between 0 and 2, like 1, that's going to be 6 minus 12, which is a negative. Now something between 2 and 4, like 3, That would be 18 minus 12, which is a positive. And now I have to compare these two number lines and figure out where we have the same signs. So let's see, from 0 to 2, A is negative, and V is not negative until you get to 1. V is negative from 1 to 3. So at least from 1 to 2, they're both negative. So I'm going to put that on there. V and A have the same sign from 1 to 2. Now from 2 to 4, A is positive. V doesn't become positive until 3, but it's positive from 3 to 4. So they're both positive then on the interval from 3 to 4. So because V of t and A of t have the same sign on these intervals, that means that the particle is speeding up. The speed is increasing on these intervals. So matching that with an answer choice, that's looking like choice D. For this problem, we're given a particle moving on the x-axis, and its position is given by x of t. In the graph above, we've graphed out x of t. We want to know what's the best estimate of the speed of the particle from at time 4. So one thing to keep in mind, because speed and velocity are often different, in this case, speed and velocity are going to be the same thing. If you look at what this particle's doing, it's always going in the same direction, or at least holding constant. So we don't have to worry about direction changes and the difference between speed and velocity. So we're basically asking, what's the velocity then of the particle at time 4? And we can estimate that by finding the average velocity over an interval that contains 4, such as the interval here from 3 to 5. So we can do x of 5 minus x of 3 all over 5 minus 3. Well, that's going to be 20 minus 20 over 5 minus 3, which all comes out to 0. So that is our estimate of the speed of the particle at time 4. And if you look at this, I mean, you know, we're at 20 whatever units this is at time 3. At time 5, it looks like we haven't gone anywhere. So yeah, you're probably going 0 miles per hour, whatever it is, on that interval. So let's go with choice A. On this problem, we have a rocket leaving the ground at time 0, traveling straight up, and the height is given by y of t, and we've got some values for y and t in this table here between times 0 and 120. Of the following values, we want to know at which value the velocity would be most likely the greatest based on our data. Okay, so let's go ahead and try to estimate this. Now, if you want to estimate velocity, one way you can do that is by finding the average rate of change of position on an interval that you're trying to estimate the velocity at. So, for example, at time 20, we could find the average velocity on the interval from 0 to 40, time 0 to time 40. It's not going to be the exact velocity, but it's as good as we're going to get using the data in this table. So then let me do average rate of change. That'll be 300 minus 0 over 40 minus 0. And I'm going to go ahead and use the calculator for this. So when I do this on the calculator, I'm going to use parentheses around the numerator and denominator and a division in between. I would normally do this with alpha y equals in fancy fraction mode, but that generally gives me a fraction back, and I want decimals on this one, which I have to do with this kind of older way of doing it. That way I'll be able to compare my numbers a little more easily. So enter, that gives me 7.5, and this is going to be, let's see here, feet per second. Now on to the next one, 40. To estimate that, I'm going to do 900 minus 105 over 60 minus 20, average rate of change from 20 to 60. And let me plug that in now. There we are. That gives me a value of 19.875 feet per second. So we appear to be going faster at that point. Let's do 60 now. That's on the interval from 40 to 80, so let's find that average rate of change. 2400 minus 300 over 80 minus 40. And it's looking like that's going to give me a value, if I plug it in, of 52.5. Well, that's way faster. All right, last interval, 80. So let's do 5,000 minus 900 over 100 minus 60. And I think this will probably be faster, but let's just plug it in to be sure. Plugging that in, we get 102.5, so much faster. Whoops. There we go. That's a little better. In any case, it's faster, so we're going with choice D. On this problem, position of a particle moving to the right on the x-axis is given by x of t. And let's see here, if x of t is a linear function, which gives the best estimate of the speed of the particle in centimeters per second at time 10. All right, well, let's think about this now. First thing to realize is if we're moving in one direction, and they said we're just moving to the right here, that means that speed and velocity are the same thing. So we can use them interchangeably on this particular problem. Now, the velocity, that's going to be the instantaneous rate of change. So that's going to be the instantaneous slope of our function. And since our function is linear, it has a constant slope. So basically, if you just know the slope of the graph, that's going to tell you what your velocity is. So looking at our answer choices, it looks like D, the slope of the graph of y equals x of t, they've got that. That's going to give us the best indication of what the velocity and the speed are. So I'm going with choice D. Looking at the other answer choices just real quickly, choice A is saying what x value you're at time 10, so that's definitely not it. B is a little bit better. This is giving you the average rate of change from time 0 to time 10. Maybe. That's assuming that your position at time 0 was also 0. In any case, this is an average velocity. This is not going to give you the instantaneous velocity that we wanted in this problem. And then choice C, this is way off base. This is just the change in x from time 9 to 11. So yeah, definitely choice D. For this one, we have a weight suspended by a spring vibrating according to this D function here. And let's see, d of t in centimeters is the directed distance of the weight from its central position t seconds after the start of the motion. All right, fine. Assume the positive direction is up. I can do that. What is the instantaneous rate of change of position? So in other words, d prime in centimeters per second at the moment the weight is first 1 centimeter above its central position. So that's a whole lot of reading. You might have to read it a few times. But basically, they're asking the first time d of t equals 1 centimeter, at that time, what is the value of d prime? So our strategy, we first have to take d of t, which they gave us here, set it equal to 1, and then solve that to get some time. And then whatever time we get out of this equation, we're going to plug into d prime. And we're going to do all this on the calculator. So let me go to my calculator now. So here in my y equals, I've entered the d of t function here in y1. And I've entered 1, the horizontal line 1, as y2. I'm just going to see where these intersect. Not really sure what window I should use, so I'm pretty sure it's going to be close to 0, though. So let me just do zoom 4. And, oh yeah, we've got this weight vibrating a whole bunch. I'm going to have to zoom in quite a bit here. Let me do my window. So there's a crossing somewhere in there. Let me just do a window between 0, because we don't really care about negative time, 0 and let's just do 1. And let's zoom fit this thing. See what happens. All right, so this looks a little easier to look at. We've got a whole bunch of vibrating, and there is the line y equals 1. Here's the first time these things intersect after 0. So let me do second trace and then intersect, option 5. And then let me move my spider closer to that particular intersection because it just picks up on the closest one you want, the closest one you have to it. So let me press enter, 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 and I get the intersection point, 0.0833 and some change. So there we are. I'm going to store that as a value A on the paper and in my calculator just so I can use it more easily. So let me quit out of the graph and let me do store. It's going to store my most recent answer. I'm going to do alpha A or whatever letter you prefer. All right. So now I just need to figure out what d prime of this time is because they wanted to know the instantaneous rate of change of position, which is going to be the derivative of this d function here. So I can do all this on the calculator as well. The nice thing is I don't even need to know what d prime looks like algebraically. Since I'm just taking the derivative at a specific x value, I can just plug it in my function here. So let me do math 8. That gives me my derivative with respect to x. And let me do alpha trace y1 is where I stored my d function. And we want this at x equals alpha a. Enter. comes out to about negative 21.765 centimeters per second, which is going to give us choice B. On this problem, we have a particle going along a straight line. Between 0 and 5, its velocity is given by v of t here. This is kind of crazy looking. And the position is given by s of t, about which we know nothing except that s of 0 is 10. All right, for all values of t from 2 to 4, we want to know at which of these values the speed of the particle is 2. So speed, we know, is the absolute value of velocity. And we want to figure out where this equals 2. We can do this on the calculator. This is a calculator problem, as this function makes clear just looking at this thing. So let's go ahead and graph this now, and then graph its absolute value and see where that intersects with the horizontal line 2. So I've entered the original function for velocity in y1. Just scroll back here so you can see the whole thing. In y2, I'm now going to enter the absolute value of this. So to get a shortcut to absolute value, you can just go to Math, Window, and abs is the first thing on the list. So we're going to do abs of, and then alpha trace to get my y1. Now I could have done this all in one function, but I like having the velocity separate just in case I need to use it for its own purposes at some point later on in the problem. All right, so, and I'm also going to unselect the velocity because I don't really want to graph that. I just want to graph its absolute value. Now in y3, I'm going to put 2, the horizontal line 2. I want to see where y2 and y3 intersect. And for my window, I'm going to use 2 to 4 because they just want values in the interval from 2 to 4. So window, x min is 2, x max is 4. Go to zoom 0, zoom fit. And let's see where these things intersect. So here is the absolute value of velocity. Here is speed. And then here is 2. So there's 2 intersection spots. To get those, we're going to do second trace, option 5, intersect. And I'm just going to press enter 3 times near each one. 1, 2, 3. That gives us 3.128. And then we'll do second trace again. Intersect again. Just move over a bit. 1, 2, 3. Now we've got 3.473. So we had 3.128 and 3.473. And they didn't give us any units for time or anything else, so we are done. For this next part, we want to find all times in the interval from 0 to 5 at which the particle changes direction. So changing direction means we have to change the sign of velocity, which means we need to figure out where this velocity function equals 0. So let's go ahead and figure that out now. Go to the grapher. On a previous problem, I had put the velocity already in y1, and I had speed in y2 and 2 in y3. I'm going to deselect those, and now I'm going to select my y1 so I can graph my velocity here. And then I want to do that on the window from 0 to 5. So window and 0 to 5. Zoom fit. Let's see what that looks like. All right, there it is. That's interesting. So it looks like we have 2 sign changes in velocity. One of them's right here. One's over here. Let's do second trace and find those zeros now. So we have a 0. I'll do left bound 0 so I don't have to keep moving over to that direction. And then we'll move the spider a little bit past it. Press enter again. We've got 0.536 over there. And for the other 0, that's going to be between, it looks like, 3 and 4. Press enter one more time. That's 3.318. So we had this spot here at 0.536 and this spot at 3.318. So that means that since velocity is changing sign at those, the particle is changing direction at these times as well. For this last part, we want to know is the speed of the particle increasing or decreasing at time 4, and give a reason. So we're going to figure out if we have the same sign or different signs for velocity and acceleration at time 4. That's how we figure out if the speed is increasing or decreasing. So let's do velocity first.
Now on my calculator, I already have this velocity function in my y1, so I'm just going to do alpha trace y1 and then just plug 4 into that to get negative 11.476. Next, I need to find out acceleration of 4. Acceleration is just going to be the prime of velocity, the derivative of velocity. So let's do that on the calculator. To do that on the calculator, I'm going to go to math 8. That's the n-deriv function. We need an x down there. In my input now, for my function, I'm going to go to alpha y1, and there's my velocity that I stored in y1. And I want this at time 4, so let's put 4 in there. Comes out to negative 22.296. Since the velocity and acceleration have the same sign, since they agree, that means then that our particle must be speeding up.